All right, question number 7 on the problem set is draw the mechanism of acetylcholinesterase. All right, so I told you guys that this is basically like a serine protease. All right, so I'm going to have, what we need for a serine protease. All right, we've got a histidine here. I'm going to just draw it with histidine with its nitrogen here and the lone pair of electrons on it. All right, so that catalytic triad deprotonates the serine, making it a better nucleophile. That does a nucleophilic attack, and we push the electrons up there. All right, this is step 1. All right, so what have we made then? All right, let's revise some of this. All right, so our histidine is protonated here. Our serine is covalently attached to the acetylcholine. All right, well, at this stage now, these electrons collapse back down, and we cleave. All right, from some acid in the active site. I'll actually have it pick up that H plus there. All right, from histidine. All right, so we end up losing now choline from this enzyme. So this whole part has just gotten cleaved off and left the enzyme. All right, so what are we left with now? Our nitrogen is again deprotonated. And we have this acetyl group sitting on our serine. Well, at this point, a water can come along. Right, we can deprotonate water to make it a better nucleophile. It does a nucleophilic attack and pushes the electrons up onto the oxygen. All right, the end result now is that we're left with this. All right, so this is a unstable intermediate. There's going to be an oxyanion hole here, stabilizing the negatively charged oxygen in the tetrahedral form. All right, that can collapse back down. Now we want to cleave off our serine, so it's going to go pick up the H plus there, leave those electrons behind on the histidine, and the end result now is that we have our serine here, and acetate can now leave the active site. So we've cleaved our acetylcholine into choline, and an acetate. My bad. All right, now for the next question. All right, how does serine end up inhibiting acetylcholinesterase? So the active part of serine that we need to worry about. Let me make sure I get the at least the active portion of this drawn correctly. Bear with me just a minute to figure out where this is in the textbook. There we go. All right, so this is the structure of serine. All right, so the enzyme is going to proceed in the same way. Histidine is going to deprotonate the serine, making it a better nucleophile. It is going to attack the phosphorus, right, push the electrons up onto the oxygen. All right, so that's going to be step 1. Well, what happens then? So our histidine is now protonated in the positively charged state. We have a bond here between the serine and this serine molecule here. All right, these electrons can collapse back down, and we can kick off a fluoride. All right, well, the end of this now is that, I'm going to redraw this methyl group, sorry. The end of this now is that we have this phosphate compound, or the rest of serine, basically covalently attached to the enzyme. All right, our histidine is protonated. All right, there's no, it didn't lose its hydrogen or anything like that. And at this point, there's not enough room for water to basically come in here and cleave this portion of the molecule off. This is permanently attached now to the enzyme because it has these two big bulky groups on it that are basically blocking water from being able to enter the active site. All right, so this is now a dead-end inhibitor of acetylcholinesterase. All right, now the last question here is, how do our voltage-gated and ligand-gated channels work together to carry electrical impulses along a neuron? All right, so the answer is basically our ligand-gated channels, they are necessary to initiate the action potential at a new neuron. All right, the voltage-gated channels are going to carry that action potential along the new neuron. Now, once that action potential has been generated first by a ligand-gated channel. All right, so how does this all work? All right, so we have kind of our presynaptic cell and our postsynaptic cell. All right, so the presynaptic cell already has an action potential. All right, so one of the things that's happening here is there are voltage-gated calcium channels that are opening in response to the action potential. All right, so this is increasing the concentration of calcium ions inside of here. Now, one of the side effects of this is that the vesicles that are sitting here at the synapse, which are loaded with acetylcholine, they begin to fuse now with the membrane. All right, so draw one that's kind of fused here. All right. And basically, they release all this acetylcholine into the synaptic cleft. All right, this acetylcholine now comes across and binds to one of our ligand-gated receptors. All right, once that receptor binds acetylcholine, it opens up and allows ions to pass through it, all right, which now starts our action potential in the postsynaptic cell. All right, once this action potential has been started over here, all right, so we kind of have, outside and inside. All right, we've basically now, so beforehand, kind of draw the before state. So before, this is sort of as time goes, right? Initially, we have a positive charge outside and a negatively charged membrane inside. Right? As soon as those ligand-gated channels open, all right, this starts to flip. All right, so we basically end up with more positive charge, not a true positive charge necessarily, but more of a positive charge inside and more of a negative charge outside. Right? This is caused by the ligand-gated channels, but as soon as our sodium ion channels see this, right, the Na channels basically are going to open up, right, and as a result, basically, they're now going to allow sodium ions to flood in. All right, so initially, the depolarization happens due to the ligand-gated channel. All right, this depolarization causes the sodium channels to open up. All right, and we end up now with sodium rushing into the cell. All right, which creates even more of a, we'll call it more of a positive charge here. All right. Now, this in turn then is going to open up the potassium channels, or K+ channels, and cause them to release potassium out at a later point in time. All right, and then it's really this movement of sodium ions into the cell along the neuron. So, as for, if I'm drawing a neuron here, so this is a single bilayer. So, this is our outside on either side here, and then the inside of the cell. All right, so once the sodium ion channels open here, these sodium ion channels open, all right, this sodium starts to diffuse along the inside of the membrane here. All right, once it enters over to the right here a little more, it causes a change in the membrane potential over here that is enough to cause the voltage-gated sodium channels to open over here. right? All right, and then those diffuse along, and that causes sodium channels to open over here. All right, so on and so forth. All right, basically every time these sodium ions basically get entered into the cell, they're going to propagate ahead and cause channels ahead of that, the action potential basically to open, and thereby propagate this charge along the membrane.